Imagine a liquid that can flow uphill, escape from containers, and even exhibit a mind-bending phenomenon known as quantum vortices. This is the bizarre world of superfluids, where the rules of classical physics no longer apply. At temperatures near absolute zero, certain substances can enter a state of zero viscosity, becoming essentially frictionless. Chapter: What is Superfluidity? About unveiling the mysterious properties of superfluids. Superfluidity is a state of matter that occurs in certain substances at extremely low temperatures, typically near absolute zero, which is approximately 0 Kelvin or minus 273.15 degrees Celsius. At this point, the substance becomes a single, coherent entity, with all its atoms behaving as a single unit. This phenomenon was first observed in helium-4, which becomes superfluid at a temperature of 2.17 Kelvin. When this happens, the liquid helium can flow without viscosity, exhibiting strange and counterintuitive behavior, such as climbing up walls and escaping from containers. For example, in 1937, Russian physicist Pyotr Kapitsa and British physicist John Allen discovered that helium can exhibit superfluidity at temperatures below 2.17 Kelvin, which is about 1/100th of a degree above absolute zero. Similarly, helium-3 also exhibits superfluidity, but at an even lower temperature of 0.0025 Kelvin. Researchers like Richard Feynman have also studied the properties of superfluids, revealing their unique characteristics, such as zero viscosity and the ability to flow without resistance, which has led to a deeper understanding of this phenomenon. Chapter: Bose-Einstein condensates, about unveiling the mysterious properties of superfluids. Another example of superfluidity can be found in Bose-Einstein condensates, which are formed when a cloud of bosons is cooled to a temperature near absolute zero, approximately 0.0001 Kelvin. This state of matter was first predicted by Satyendra Bose and Albert Einstein in the 1920s, but it wasn't until 1995 that the first Bose-Einstein condensate was created in a laboratory by Eric Cornell and Carl Wieman at the University of Colorado. At this point, the bosons occupy the same quantum state, forming a single macroscopic wave function that exhibits superfluid behavior, with around 2,000 rubidium atoms behaving as a single entity. The creation of Bose-Einstein condensates has led to a deeper understanding of the properties of superfluids, with scientists like Wolfgang Ketterle also achieving this state with sodium atoms, and has opened up new avenues for research in quantum mechanics, with potential applications in fields such as quantum computing and superconductivity. Chapter: Quantum Vortices, about unveiling the mysterious properties of superfluids. One of the most fascinating properties of superfluids is the formation of quantum vortices, which are essentially tiny whirlpools that can form in the liquid. These vortices are created when the superfluid is rotated, causing the liquid to form a series of quantized vortex lines, typically around 10 to 100 nanometers in diameter. The study of quantum vortices has led to a deeper understanding of superfluidity and the behavior of liquids at the quantum level, with researchers such as Richard Packard and Russell Donnelly conducting extensive experiments on the subject. For example, in 1955, the discovery of superfluidity in helium-4 by Pyotr Kapitsa and John Allen demonstrated the unique properties of superfluids, including the formation of quantum vortices. Since then, studies have shown that quantum vortices can be stable for over 10 seconds, with some experiments observing up to 1,000 vortices in a single container. The understanding of quantum vortices has significant implications for fields such as materials science and quantum computing, with potential applications in the development of ultra-sensitive rotation sensors and quantum devices. Chapter: Superfluid Helium, about unveiling the mysterious properties of superfluids. Helium-4 is the most well-studied superfluid, and its properties have been extensively researched by scientists such as Pyotr Kapitsa and John F. Allen. who first discovered its superfluidity in 1937. At a temperature of 2.17 Kelvin, helium-4 becomes superfluid, exhibiting a range of strange and exotic behaviors. For example, it can flow through tiny openings with zero viscosity, and even climb up the sides of containers, defying the force of gravity. This phenomenon, known as the creeping film effect, has been observed in numerous experiments, including those conducted at the University of Cambridge and the Massachusetts Institute of Technology. In fact, studies have shown that helium-4 can flow at speeds of up to 1 meter per second through openings as small as 10 nanometers in diameter. This phenomenon has been observed in over 100 experiments worldwide, and it continues to fascinate scientists to this day. With ongoing research at institutions such as the European Organization for Nuclear Research and the National Institute of Standards and Technology, the study of superfluids has led to a range of potential applications, from quantum computing to advanced materials science. By understanding the properties of superfluids, scientists can develop new technologies that take advantage of their unique behavior. For example, superfluids could be used to create ultra-efficient cooling systems, with the potential to reduce energy consumption by up to 50%. Researchers such as Dr. John Doyle at Harvard University are also exploring the possibility of creating superfluids at higher temperatures, which could lead to a range of new and exciting applications. In fact, scientists have already successfully created superfluids at temperatures as high as 2 Kelvin, which is significantly higher than the typical temperature range of most superfluids. Additionally, companies like Google and IBM are investing in superfluid research with the goal of developing new types of quantum devices, such as superfluid-based quantum computers, which could potentially solve complex problems up to 100 times faster than current computers. With continued research and development, the potential applications of superfluids are vast and exciting, with the potential to revolutionize fields such as medicine, energy, and technology. Thanks for joining us on this journey into the mysterious world of superfluids. If you're curious about more mind-bending phenomena, be sure to subscribe to our channel and check out our next video on the strange properties of metamaterials.